All right, let's start. Hello, everyone. This is Dr. Yuzo, and this is ECE 318 lecture. The third lecture for this semester. And first of all, can you guys hear me well? And also being able to watch my shared screen? Okay, thank you, Daniel. All right, thank you, Shane. All right, so first of all, we are watching the Gantt chart, being understanding or being clear about where we at. Okay, we are at this particular cell. Yeah, we are at this particular cell. Okay, so supposed to be the last lecture for the module 0 about the review. And if some concepts left, I'm gonna squeeze it into the beginning of the module 1 by next Tuesday. Okay, so this is the plan. All right. So this is the example 3, was the end of last lecture. We talked about one circuit, electronic circuit. And actually in example 3, we're gonna have 2 more examples, small examples to show you or say help you become familiar with the electronic circuit schematics. And because in the future real job, you're not gonna see some circuit like this, okay? No one's sketching the circuit schematics in, say, PCB software in this way. No, you won't be able to see the loop, okay? Instead, you're gonna see something like the circuit we learned from this example 3. Okay? This is the first one we have done, okay? And so what you see is instead of voltage source in the circle, we are seeing a voltage bus here. Voltage bus is nothing but provided by voltage supply, 5 volts bus, okay? And all the way down to the ground. Maybe not even ground if something more tricky. But anyway, along this path, you have multiple components occupying certain amount of voltage. And the idea is called from top to bottom KVL. Or say the pass KVL. Because the KVL we learned from 235 was called loop or say mesh KVL, right? And without seeing the loop or mesh, you probably feel a little bit confusing or at least not familiar with it. However, such kind of circuit is containing a loop like this, all right? So by using the red colored wire connection, I'm showing the essential loop contained. Right? So there is a loop. However, after become familiar with the look of the circuit, we know we just use the so-called pass KVL. What it means is from the top voltage, which is 5 volts, to the bottom voltage, 0 volts, the total voltage drop through this path we easily know as 5 minus 0, 5 volts. And equals to the summation among all of the component voltage. And of course, be very careful. The polarity is very important. Since you are using 5 minus 0, that means the voltage drop is from top to bottom downwards. And following the same direction. The voltage drop through 20 kilo ohm must be downwards as well. Therefore, we have polarity like this. Okay. Same thing here. We are talking about voltage drop in this way too, and luckily is positive here, negative here, as given this 0.7 voltage source, DC voltage source. So it's nice. So 5 minus 0 equals to this voltage this way, plus voltage this way as well. This is how we come up with this pass KVL equation, in where only one unknown, which is I naught. Okay, we can find the current downwards, again, downwards. Okay, it must be downwards. And then V naught is very easy. V naught is here with respect to the ground again. So the positive is here, negative is the ground. Exactly same voltage as this 0.7 voltage source. So we are done about this I naught and V naught here. Okay. So two more small examples like this to get used to this past KVL. Okay. Let's see what is a second circuit. Second circuit, obviously, more complicated, but let's see. Tricky thing is, what top positive 5 volts remains. However, bottom is not ground. And actually, entire circuit, you're not seeing a ground at all. Okay, get used to this. Get used to this. Okay. Again, top positive 5 volts, bottom negative 5 volts. Two buses. In the middle, we have two resistors and 1 voltage supply. And what we know is voltage supply remains as 0.7 volt, and this resistors are respectively 40 kilo ohm and 53 kilo ohm. Now what we're gonna try to find out are I naught, like this, downwards again. V naught 1 and the V naught 2. So now just give you guys kind of 5 minutes to try this over yourself. Okay. Go as far as you could and follow the past KVL idea to come up with some equations. Let's see where you can reach. Okay. 3 unknowns to be found. I naught, V naught 1, and V naught 2. Okay. So I will present the solution in around 5 minutes. Okay. All right, carry on. Of course, meantime, if you have any questions, bring it up. Okay, bring it up. So, waiting any questions. Otherwise, I will show the solution in 5 minutes. Anyone get any value for any of these three unknowns? Any result? They Kevin got I naught like a 0.1 something milliampere. It's basically right. It's right. It's right. Yep, that's a correct I naught. I just got 0.1 milliampere. I think it's a rounding issue. That makes the difference between mine and his. All right, now we got I naught. Anyone got any V naught 1 or V naught 2? All right, let's see the solution together. Okay, let's see the solution together. First of all, we call it pos KVL. Right, pos KVL means again from the top to bottom. Well, you might wonder, can I go from the top to bottom to top? And can you go from the bottom to top? Of course you can. Okay, it doesn't matter which way. The direction doesn't matter. The point is keep that direction consistent on both sides of the equal. Okay, that's the key. So if you just assume from top to bottom downwards pos direction, and then what we have is 5 minus what? 95, right? From top to bottom, 95, the span is obviously positive 5 to 95, the span is 10, right? So 5 minus 95 equals to what? 40K times I naught. Okay, introducing the voltage like this. Plus 0.7 voltage polarity like this. Be very careful. Okay, voltage polarity must be like this. And then plus the voltage cross 53K. Once again, one equation, one unknown. Enough for us to find and know that it turned out to be 0.1 milliampere. Right? Any questions regarding I naught? All right, if this is fine, then we move on for V naught 1 and V naught 2. Actually, there are more than one way to find out them. However, my way to find out them is remaining pos KVL idea. However, of course, it's different KVL. Another pos KVL. Because the pos, you can choose any part of the circuit to write a pos KVL. It doesn't matter, right? So how about I choose a pos from 5, the top, down to this V naught 1. I just choose this pos, okay, from top 5 down to V naught 1. The total voltage drop is obviously 5 minus V naught 1. And along this pos, you only have one component, which is 40K ohms resistor. So the voltage will cross it, which is equal to 40K times I naught, according to the Ohm's law, is the voltage will cross it, and equals to 5 minus V naught 1. Does it make sense? And the folder equals to 40K times 0.1 milli. From here, one equation, one unknown. V naught 1, we got 1 volt. Does it make sense? Feel free to use another pos like from V naught 1 down to the negative 5 volts. That's absolutely fine. If that way, and then V naught 1 minus negative 5, right? And equals to what? 27 volts plus 53K times I naught. Okay. You end up with same result for V naught 1. Does it make sense? So choose any path to write KVL. It's very flexible. Okay, this method, or say this idea, is very flexible. Okay, always work. Always work. Any questions regarding this V01? All right, if this works out, then the last one is V02. What's the easiest way? Well, again, more than one way to find out V02. Okay, again, more than one way. What's the easiest one? Maybe neither way is difficult. However, I'm seeing we're still applying past KVL. Well, V01 minus V02, this pass, along this pass, what? Only 1.7 volts in the middle, right? And then easy enough to find V02 as 0.3 volt, right? Again, past KVL always work. It works maybe if you have a very complicated circuit. One past KVL is not sufficient. However, past KVL always work. Okay, always work. So maybe you need more. It's just a matter of how many you need. Okay, so past KVL always work and very flexible. Does it make sense? Choose any path and then taking care of the voltage drop, total voltage drop, equals to the sum of the voltage drops through the path from all of the components involved, right? This past KVL. Any questions regarding this circuit? All right, if this is fine, then one more exercise, and then we can move on to the next thing. So third circuit is like this. The third circuit is, again, I'm trying to make the circuit look similar so that you can circuit. And let's see, I naught and the V naught. All right, so another 3 to 5 minutes for you to exercise. Okay. Remember to fully utilize it. There's nothing more useful and more effective than the in-class exercise. Okay, there's nothing more important than this. Okay, it's very, very useful.
With how you drew that battery, is that the negative terminal closer to the 5 volts? And
Correct. Correct. In other words, this is a short bar. This is a longer bar. Yep. Polarity, direction of the current and polarity of the voltage always play a very critical role. Okay. Always play very critical role. Any result? Anyone get? Yeah, Shane got the correct I naught value, 0.5, around 0.5 milliampere. V naught is correct as 5.7 volt as well. Good job, Shane. All right, so basically the pass from top to bottom pass KVL is like this, right? 5 minus -5. Total is 5. Total is 10. Right? Then you could go through. You find this is a negative polarity. This is a positive polarity, which is the opposite. So there has to be negative 0.7 here. And then due to the I naught, they introduced the voltage across 20 kilo ohm as positive here, negative here. Perfect. So positive 20 kilo times I naught. Right. So this is the pass KVL. Okay. So the key is this negative 0.7 volt. Okay. It must follow this direction. Otherwise, your polarity must be reversed. Okay. And next, you just pick any pass KVL you feel comfortable with to find out V naught. Obviously, we have multiple choice, right? So this one pass, this is another path, right? So if you choose the top one, and from top 5 down to V naught, the total voltage drop is equal to what? -0.7 volt, which gonna give you V naught as 5.7 volt. Does it make sense? You choose the other path, of course, same result, guaranteed. Okay. Think about it. Any questions? Well, if no questions, try to do this in 1 or 2 minutes. What is the equivalent circuit here to the loop? What I'm saying is this. Remember what we have done here? From this circuit, we find out the loop, right? So in this circuit, what is the equivalent loop circuit? Loop look. Spend 1 or 2 minutes. Go ahead. So it's like this, right? So the key is the 5 volts, how to interpret the 5 volts. Right? This is the 5 volts on the top. This is 0.7 volts remains. So does the 20 kilo ohm resistor. And then we are reaching the negative 5 volt. So this terminal is what? Here is what? Oh, I'm sorry. This is backwards, right? Completely backwards. This is a mistake. Much better, isn't it? Does it make sense? Top one is short bar, okay? Bottom one is here. This guy is longer bar. Okay? So bottom one here is positive. Top is negative. And what is this terminal? Yes. What is it? Anyone? This terminal is what? No, this terminal is not 5 anymore. Here it's 5. Here is positive with the 5, feeding the rest of the circuit. So here is what? Exactly. Okay, it's 0 volts, which is the ground. Exactly. And Daniel is correct. Okay, it's the ground. Does it make sense? And then go down to here. So this terminal is the negative one feeding the circuit. Here is positive. And the voltage magnitude is 5 as well. So this terminal is what? This is what? Exactly. 0 again. Feel free to short them together. Right? Short with this ground together. This is what we did in the lab 1. Remember how we connected positive and the negative power supply to 741, the chip? Remember what we did last week? Right? So once again, the positive is here, feeding the rest of the circuit. Negative is here as the ground, and the magnitude is 5 volts. Therefore, this is equivalent to here. On the bottom, the negative is feeding the rest of the circuit with negative terminal polarity. Positive polarity here is shorted to the ground. So this is how we deal with it here. So take a look. This is how we see the loop. Okay? How we see the loop. And if you're interested, you can write a KVL which you are feeling maybe much more comfortable with from the 235 inside of this loop. You can end up with same result. You're gonna end up with same result. Okay. So this is how we see the loop. Of course, there is a loop. Otherwise, if there's no loop, open circuit, then there's no current. And meaningless. That circuit is meaningless. Of course, there is a loop. However, in such circuit schematics design, we don't show the loop. Okay? We are not seeing any loop. Okay. So any questions regarding this pos KVL idea? We're going to use this skill quite often through the rest of the semester. So any questions, concerns? All right, now we can move on here. We can move on here. Coming back to the PowerPoint slides, talk about the example 4. Example 4. What is example 4 here? Example 4 here, what you'll be seeing is two sources and with two resistors, one inductor and one capacitor. Okay. And a little bit similar scenario we came across in the lab, right? So we are not talking about the resistance, inductance, or capacitance. Instead, we are talking about impedance. That's why we are using Z. Z, capital Z, is representing the impedance. Okay. And why we are doing so? Because the sources are what? Both sources are what? AC source. Yeah, AC source. And the one is current source. The other is the voltage source. Okay. And independent or dependent here. Independent source or dependent source. Anyone knows? Independent. Yep. Connor is right. This is nothing but independent current source and independent voltage source. Okay. No trick here. No trick here. And we're looking for V1. We're looking for V1. Actually, looking for any voltage or current inside of the circuit. Not a big deal. What we're trying to review is superposition principle. Yeah, superposition principle. First of all, why we are thinking of using superposition? Why? Anyone can explain why we are thinking of this method using superposition for what? Why is that? Two sources, exactly. Daniel is right. Okay. We have two sources, so we might think of using superposition. So according to superposition, what do we do? This, right? So keep one independent source while eliminating the other independent sources. Here, there are two things you need to be very, very careful. You're keeping one independent source, okay? And then eliminating the other independent sources. Always independent. Because if you are seeing any presence of dependent source, you cannot touch. You cannot touch. It is always there. Okay, it's always there. Keep it there. No touch. Okay. Eliminating the other independent source, you can do so. Okay. However, you can't eliminate any dependent source. Okay, that's absolutely not okay. You have to leave them there. Okay, you can't eliminate any dependent sources. Second thing is, what does it mean by eliminating? What does it mean, or say, what specifically, what we do? How to eliminate? Anyone remember? Just to speak out, okay, that's going to be much more efficient. How to eliminate? What's the idea?
Short out voltage sources.
And an open current.
Excellent. Combining Josh and Kevin together, and then we got the correct answer. Very good, very good. So again, to the independent source, if it is a voltage source like this, how to eliminate it? Short it. To the independent current source like this guy, what do we do? This is short circuit. Okay, SC. What do we do? Open it. By the way, why two independent voltage source we shorted and the two independent current source we open it? Why is that? What is the reason behind? Anyone knows?
So you take each source down to zero, basically.
Yes, basically Connor is right. Connor is right. Short circuit, just recall, what is the voltage across a short circuit? What is it? Nothing but 0. Then what is the current through the open circuit? 0, 2. Remember? This is why we are short and open the voltage source and the current source respectively. Okay, this is the reason. It has reason. Okay? Everything has reason. Okay, that's the reason. Short circuit voltage is 0. You are making that voltage to become 0. That is called eliminating. Your open circuit here make that current become 0. That is eliminating, right? That pretty much make them really 0. Okay, that's the reason. By the way, what's the voltage across an open circuit? Anyone knows? What's the voltage across the open circuit?
Anthony?
Any other answer?
Oh, 0.
0? No. What's the voltage across the open circuit? We know the current across the open circuit is 0. And then what's the voltage then?
Wouldn't it just be whatever that voltage was? Like if you go up to a receptacle in your house, it's technically an open circuit, but it still has 120 volts across it.
Kevin is basically right. So what's the correct answer? Actually, make it easier. What's the correct answer? The voltage across open circuit is what? Unknown. Unknown. Okay. Absolutely not necessarily 0. Absolutely not necessarily 0. Okay. It's unknown. It's all depending on the rest of the circuit. Does it make sense? So keep this concept very solid. Okay, open circuit, you can only know the current is guaranteed to be 0. What's the voltage? No, you don't know. Okay, don't even guess. It all depends on the rest of circuit. Okay. Similarly, what's the current through the short circuit then? What's the current through the short circuit here? Same thing, unknown. Absolutely not necessarily infinity. Okay, absolutely not necessarily. Okay, all depending on the rest of circuit. Okay, so keep this open circuit and short circuit concepts clear. Okay, we only can guarantee 0 current for open circuit. We can also guarantee the 0 voltage across the short circuit. We cannot guarantee anything else. Is it clear now? All right, thank you, Shane. Okay, we can move on. Okay, so this is a little bit of review of the superposition and specifically what we do. First, what are we doing here? This is pretty much keeping the current source. Meantime, eliminating what? The voltage source. Short it out, you see? Short it out, what's the consequence? Your voltage becomes 0, as we just said. And then inside of this circuit, you're looking for what? V1, right? And then what do? You keep the voltage source and open, or say eliminate the current source. You see? So split the original circuit into two individual circuits, right? And then from the second circuit, you're looking for V1 as well. Of course, 2 V1s are different. And the total V1 we are looking for in the original circuit equals to what? What? This V1 plus this V1. Okay? This is what the superposition did. Yeah, this is what our superposition did. Okay, the total original V1 just equals to this V1 plus this V1. Okay, superposition. All right, any questions regarding the superposition? This is one of the important circuit principles. or say circuit analysis skills you learn from 235. Right, next thing very important in 235 is the voltage and current dividers. Okay, I'm gonna go to the doc cam so we're gonna write some notes here. Okay. Voltage and current dividers. Trust me, it could be very easy, but sometimes it could be very confusing. Let's see. Once again, this is example 5, and you have some circuit here. Okay. Let's talk about the voltage divider first. In parallel, we can talk about current divider. I want to place them two together. It's easier to clarify some tricks. So the first circuit is as simple as this. Total voltage source V with R1, R2 series connected. And if you're looking for V1 and V2, what they are? V1 as easy as total voltage times what? Who's the numerator? Who's the numerator? R1, right? With the denominator, R1 plus R2, right? Similarly, V2 equals to V times R2 in the numerator, and R1 plus R2 remain as the denominator. Any questions regarding this? This is a little bit reviewing the very basic voltage divider. Of course, very important. The voltage polarity must be like this. Say V2 is labeled as such polarity, then how do you find V2? You need to have a negative sign in front of the result like that, right? So voltage polarity, again, very important. Yeah. Let's see the second one. Total voltage remains as V. Resistor becomes R1, R2, and R3. And now we don't have to find all of the three voltages, V1 through V3. We just need to find, say, V1 equals to what? I'll give you guys 1 minute to write this down. 1 minute. Go ahead. V1 equals to what? Not something difficult, right? V times, and again, is a resistor ratio. In the numerator remains as R1 itself. Denominator is R1 plus R2 plus R3. Okay. V2, V3 follow the same idea. Okay. Just to vary the numerator here. Okay. And of course, if you have R4 here, one more, you're going to add R4 here correspondingly. Okay. Now, how about this case? Now V1 equals to what? V2 equals to what? Another 1 minute, another a minute to write this down. So V1 equals to what? Anyone? Yeah. Here we go. Okay. A little bit tricky, especially since we are talking about a voltage divider. However, these R1 and R2, they're parallel, not series connected at all. So when you cross a voltage source V across them parallel, guess what? The voltage remains same because, again, parallel, not series. Okay, don't be confused here. This is actually not a voltage divider at all. It's a tricky question, a little bit tricky. But I'm mixing this circuit with the rest of the voltage divider. Try to make you feel like easier to differentiate it. Okay. Yes. Don't be confused. This is not even the voltage divider. It's not. In other words, the V total V is not shared by V1 and V2. No, it's not shared. They both have V because, again, they're parallel. They're parallel together and then parallel with the source. Yeah, good. Yeah, so Shane got the right answer too. All right, next one. How about this case then? And now, V1 equals to what? V2 equals to what? And V3 equals to what? Give you guys 2 minutes. 2 to 3, maybe 2 to 3 minutes. All right, let's see the solution here. So V1 equals to what? Total V times a ratio. Numerator is R1 itself. Denominator is R1 plus what? R2 parallel with R3. So you can tell you're going to calculate R2 parallel with R3 first, and then add onto R1 as the denominator. Okay. And then V2 equals to what? Total voltage again, times, who's in the numerator? Anyone knows? V2. Who's in the numerator here?
R2.
Any other answer? Is no, it's not R2. Who's in the numerator? Very good. Daniel is correct. R2 parallel with R3. How about denominator? Remain same as R1 plus R2 parallel with R3. Yep. And the V3 equals what? V3 equals what? Anyone? Same as V2. Very good. Good. So let me summarize the volt divider, how you should think, how you should conduct it. Remember, first thing is two things, and the two things only, okay? Second thing is series connected to share the total voltage. Okay. Here I'm emphasizing two things. One is you are only dealing with two things, okay? Two resistors, we'll say, or two impedances. Okay? No more than two. Second is series connected. Well, second, the series connected is easier to understand. However, what I mean by two things and two things only. Look at the first circuit. It's the series connected two things and only literally two resistors there. You don't need to do anything directly. Voltage divider. Look at the second circuit. You have three things, three resistors, R1 through R3. So what do you need to do? You need to do combination. What does it mean is you're looking for the V1 and then you need to keep R1 here in the denominator. Combine the rest of the two, which is R2 and R3. Since R2 and R3 are series connected, that's why you have R2 plus R3. So again, your denominator only stays two things, summation of two things, no more, okay? Even though you're seeing R1 through R3. However, the idea is you're combining R2 and R3 first. Okay, same idea apply onto this V2 and V1. If you're looking for V1, of course, you're going to keep R1 as itself, as one thing. The other thing is you have to, no matter what, combine R2 and R3 together, becomes one thing. You see here? So the denominator is and always is the summation of two things. If more than two things present, what you need to do is to combine. Same idea. V2, how to find V2? Total voltage times the ratio. In the numerator, well, in the denominator is R1 series with the combination of R2 and R3 in parallel. Okay. Because two series. Well, R1, there's no way to combine with anyone else. Doesn't make sense. Because R1 here is series connected with this parallel. You can't easily combine R1 and R2. No. You can't do that kind of combine. You can only combine R2 and R3. And then the result is a parallel resistor here, series connected with R1. Right? So to find V2, you total voltage times the ratio. The numerator is the voltage you're looking for, which is obviously the combo of these two. The combo of these two. And the resistance is R2 parallel with R3. Denominator is R1 series with this combo. So R1 plus R2 parallel with R3. Does that make sense? So I'm emphasizing two things. Must be two things. If more than two, do combine. Do combine. Okay, combine them together. Okay. Combine them together. Yes, of course. As Kevin said, V2 is also equals to V minus V1. Yes, that's nothing but correct. Okay, V2 equals to nothing. V2 equals to V minus V1. That's absolutely correct. Okay, absolutely correct. Yeah, because V2 voltage is the voltage cross this combo. Okay, plus the V1 here equals the total voltage. No problem for that. No problem for that. So this is the voltage divider. Voltage divider. In parallel, let's see the current divider. We once again begin with the basic one we learned. From where we can easily tell I1 equals to what? Total I times, who is the numerator? Who is the numerator here? Anyone? Numerator is what? Anyone? Numerator is the other branch. Is the other branch, which is R2. Correct. That description is accurate. Okay. You're looking for the branch here, current, which is I1. Your numerator must be the other branch resistance, which is R2. And denominator is R1 plus R2. Similarly, I2 equals to total I times R1 over R1 plus R2. Okay. The other branch, exactly right. Okay, the other branch. This basic one. Next. You have three resistors in parallel. So now what is the I1? Give you guys 1 or 2 minutes to write this down yourself. What is I1 now? All right, it equals total current times the ratio, right? Numerator is the other one, R2, R3. Denominator is R1 plus R2 plus R3, right? Right? Absolutely not. Okay, absolutely not right. Okay, no way for this to be right. Here is actually emphasizing once again the two things and two things only. Okay. In other words, if more than 2, you need to do the combination. You need to combine. Becomes 2 left. The second is must be parallel. Connected to share the total current. Okay. It's the principle. Therefore, I1 equals what? Total current times a ratio. You need to do the combine. Okay? So obviously, you once again combine R2 and R3 because you need to keep the R1. You're looking for the current through it. You need to keep R1. You can't combine R1 with anyone else. So the numerator is the other. The other is what? The other is the combo of R2 and R3, since these two guys are parallel. So you need to parallel them to combo. Okay, so this is the other, the so-called the other branch. And the numerator, denominator is what? R1 itself plus the second thing. Right? Only 2 things in the denominator. Only 2 things. Okay. If not, if more than 2, you need to combine R1 plus who is the second thing with the other thing. So once again, combine between R2 and R3. Take a look and see if it makes sense. If it does, then what is I2 then? Similarly, a ratio. Denominator is R2 this time because you need to keep it here. You can't combine R2 this time because you're looking for I2. So you need to combine R1 and R3. These two guys are parallel, right? And then in the numerator is the other. So who is the so-called the other branch to R2 branch? R1 combined with R3, right? That makes sense. So this is the current divider. The current divider. I3 follow the same idea. I3 follow the same idea. Any questions? Sure. All right, if this is fine, then move on to the next.
Well, actually, Dr. Zhao, I was wondering
Yeah.
if there was any good way of thinking about that, like some intuition as to why that works, because it just seems so strange. That would be the other branches.
There what?
I was just kind of wondering why that equation works like that.
Oh, like I said, the current divider as well as the voltage divider, you always remember there has to be 2 things. 2, okay? But these are 3 branches, not 2. So you need to combine any 2 of them. Okay? So how to combine? If you're looking for I1, you don't want to combine R1 with anyone else. So you need to combine R2 and R3 together. R2 and R3 are parallel. So this circuit pretty much becomes, you keep R1 as I said. Second branch becomes what? R2 parallel with R3. Make it 2. See it? Make it 2.
Yeah.
And then in the equation, only this 2. Denominator going to be R1 plus R2 plus R3. Parallel with R3. Numerator is the other, which is R2 parallel with R3 times the total current. This is the I1. Does it make sense how it comes?
Yeah, that makes sense. I guess
equation,
I guess I was wondering originally because it's like you're using for like the art for like for example the first when you first did it, how it was like the opposite resistor. And I think it's interesting. I don't know if I thought how it's like the opposite branch that you're actually kind of like solving stuff for. I don't know.
It's out of here. Okay, two things. Always two things.
Okay.
It's don't try to remember or say memorize the formula. Now, don't count them as formula. No.
Mhm.
If you count them as formula, you're gonna be confused. Okay. And try to understand this. Try to understand this. These two principles. You're looking for only two things. Okay. If more, you have to combine. Okay. So this is the principle. We try to follow the principle rather than memorize the result here, the equation here. And then it will make sense. Okay. If you memorize the equation here, it's actually no, it doesn't make much sense.
Yeah. Okay, thanks.
Sure. And then the third circuit here is what is once again it's tricky question, right? I1 equals to I2 equals to I. Series connected to two resistors violating the second. Here, okay, you're talking about current divider. Okay, it must be two things in parallel, okay, rather than two things in series. Okay, two things in series sharing exactly the same current. Okay, it's not current divider. It's not current divider. It's not dividing the current. Okay, they're having the exactly same current, right? All right, here. Last one. All right, I gave you guys 3 minutes. Find I1, I2, and I3. Go ahead. Conduct this exercise. Find I1, I2, and I3 in this last circuit. 3 or 4 minutes. Okay, go ahead. Now here, Kevin is trying to explain the question from Connor previously. Probably Connor was asking why is the other branch in the numerator, the other branch in the numerator. You can think in this way, okay? You can think in this way. These two are parallel, right? Parallel. I share the total current. Two parallel, then what happened is they have exactly same voltage. Does it make sense? R1, R2 here have exactly same voltage. So tell me, let's assume R1 is bigger than R2. Okay, R1 is bigger than R2. The same voltage here, according to Ohm's law, I1 and I2, who is bigger? Who is bigger? Obviously, I2 greater than I1, right? So you have smaller resistor, you're gonna have bigger current. Bigger resistor, you're gonna have smaller current. Does it make sense now? So it is the other, because they have same voltage. And the voltage divided by resistance, rather than times resistance, equals the current. Divided by resistance, so resistance is in the denominator. So the bigger one gonna result in a smaller current. The smaller resistor in the denominator gonna result in the bigger current because of the Ohm's law. Once again, parallel, so same voltage, right? Does it make more sense now, Connor? And Kevin?
I'm getting there.
Well, maybe you guys are working on the on this explanation, but by reviewing the recorded lecture, you probably can follow. All right, let's take a look at the solution here. So I1 equals to what, first of all? I1 equals to what? Anyone? Yep, Shane is right. Shane is right. Be very careful. R1 is not dividing the current. It's not part of the current divider. R1 is series with the current source. So the current through R1 is nothing but the current source current. It's a series connected. It's not a current divider. Good. And then I2 equals to what? I2 is dividing the current with R3. So I2 equals what? Total I times the ratio. Okay. Again, R2 and R3 are dividing the current as this. I1 and R1 is not part of the current divider. R2 and R3 are. Any questions? Anything? All right, if this current divider makes sense, then come back to our PPT. Well, after reviewing what are the current dividers, okay, let's either review, no matter which case is to you, is either review or just learn a little bit basic AC and phasor. So one AC sinusoidal time domain expression like this is equivalent to a phasor. Because from the sinusoidal, we know the capital M is what? Magnitude, right? Omega is angular frequency, theta is the phase angle. Okay. And it's corresponding to a phasor in where we have magnitudes and angle of phase angle theta. Okay, this is how we convert sinusoidal to phasor. Very simple, very simple. A very simple representation. Okay, but in the phasor, you can't see the angular frequency. Obviously, you can't. Okay, can't tell that. But it's okay. And such phasor is equivalent to a rectangular or say complex number. Okay, phasor is equivalent to a complex number in such way. Okay, this conversion between the phasor and complex number. Complex number also could be called a rectangular form. The phasor is called the polar form. Okay, two different names. Okay. And a little bit exercise here to find a phasor from find a phasor form. The given here is 15 as magnitude. 300 is omega, angular frequency. Pi over 3 is the phase angle. No problem, very clear. However, this is not sine, but cosine. To be very honest, if you convert the cosine to the phasor directly, that's fine too. However, if you trying to keep consistent that you just consider sine here as the phasor directly, then you need to do a what? Plus 90 degree, right? Plus 90 degree. To convert cosine becomes sine, you need to do add 90 degree on. The rest of the magnitude, the frequency remains same, right? And from here, you convert it to the phasor. So the phase angle for this sine is what? Pi over 3 plus pi over 2, which is 150 degree. Okay. This is a little bit complex and the phasor representation for the AC. Not the core content of this course, not at all. Okay? This is 335 and 341 knowledge, but here I just bring it up. Okay. And here impedance. These are the things we have discussed in the lab. Okay. Impedance of the resistance is nothing but the resistance itself. Impedance of the inductance equals to J omega L. And the impedance of capacitance is equals to 1 over J omega C. And further, it's equals to negative J over omega C. And of course, omega is the angular frequency, is equals to 2 pi f. F is the frequency. So in AC circuit, the impedance of the inductor and the capacitor are frequency dependent. Why so? Well, just look at their impedance value. They're in terms of omega. Of course, further in terms of F. Therefore, of course, frequency dependent. Because in their impedance expression, there's an omega F there. So of course. And the frequency is the frequency of the AC source. So remember in the lab, 500, 10 kilo, and 500K frequency, where we are tuning it, where we obtaining those frequency. We're tuning the signal generator, right? Which is the source. Okay. So every time you mention the AC circuit frequency, where does it come from? Or say, who is determining that? Source. Okay. Source frequency is the frequency we keep talking in the AC circuit. Okay. So this is basically the concept of AC, and here is an example for finding the impedance of resistor, capacitor, and inductor. And I leave this as yourself to do after class exercise. Okay. So basically that's all for today. And just the one thing, I published a exam time survey. Let me show you, where is it? It's here. As part of at the end of the module 1. Okay, go to the module 1, and then you will see it at the end. Okay, this is something you have to conduct. Okay, provide me a survey feedback about if the planned exam time is okay to you. Okay, let me know from there. And you have to submit this survey, okay? Without submitting this survey, you're not able to access the material for the following modules because I'm setting it to be the requirement, okay? So please conduct this survey and let me know your feedback as soon as possible. Well, the due date is quite a while later. However, just do it as soon as you could. Okay. And a test run exam going to be published soon, later as well. Okay. Before our real midterm, of course. Okay. All right. Thank you for attending today's lecture, and talk to you guys next week. Okay. Bye now.